All right, welcome back, everyone. So we are now going to move to a panel on agriculture and environment intersection with GenAI. And in a way, this is a continuation of the discussion you just had before the break. So you will see some of the same issues that ecologists were interested in, and some of the things from the morning as well, right? So my name is Shashi Shekhar, and I will briefly say a little bit about my background, mostly from spatial computing. And then we have the panelists here. Maybe Baskar, you can say, just raise your hand. So Baskar is from Iowa State University Applied Mathematics, but he also is serving as PI for one of the 5 Ag AI institutes called AIIRA around resilience. So we'll learn more about it. Deborah, please just wave everyone. So she comes from University of Southern California with expertise in climate science, and as we know, that interacts a lot with agriculture and environment and so on. Professor David Mulla. Professor David Mulla is from University of Minnesota. He led Precision Agriculture Center for a long time, and he's also a very core member of the AI Leaf AI Institute as a co-leader. So we'll learn a lot of agriculture perspective. Then Professor Shen, could you just wave? He's coming from Penn State University and with expertise ranging in environmental systems and also KGML kind of work. Also, I wanted to mention 4 other people. So Professor Yao Chiang, if you just wave. So he's is basically a co-moderator or co-organizer. He shaped the questions and again has a great background in GI science, working on many environmental problems, also part of AI Leaf. And if I may call on some people in the audience, Dimitris, would you stand up and just say hello? So from John Deere, a true blue agriculture company, and Centera. Also from computer vision background, so great resource. Bob Bennett, if you would please stand up and say hello. He's from US Forest Service. So any forestry question, we may go to him. So, great expertise. And Ricardo, if you could just stand. All right, wonderful. So AAAS Science and Technology Fellow at USDA REE, ARS, which is their in-house research, right? And he actually help the ARS leaders to do an inventory of all the AI use cases and plans within ARS. Couldn't get clearance to present his slides, but I hope he would be willing to share some things verbally that he's allowed to, right? And in addition, in the morning panel, we had a few other people. Professor Zopa, if you can just stand up and wave, if he's still here. So he's with another Ag AI Institute led by Washington State University. And Aryan, who is a co-organizer of the workshop, if you can just wave, you finished your PhD from there, right? Your advisor, Dr. Jopa, is there. So there is a fair amount of agriculture presence in the room with both sides, people who are true blue agriculture and people who are doing AI in context of agriculture. So it can be a very rich discussion, right? So the other part I wanted to connect to is what Vipin mentioned in the beginning, the America's AI Action Plan. And we all expected a lot of AI in there. But does anyone know how many times agriculture was mentioned in this document? At least once. So at least more than once, actually. So it does talk about adoption issues. And Ricardo was also mentioning this, right? We can have all the fancy technologies. When you go to farmers, are they willing to adopt it? They have very unique challenges. Some of that we heard on the ecology panel. The heterogeneity is all over the place in this place. In fact, spatial statistics. Initial funding came from USDA at Iowa State and North Carolina. And a lot of those ecology issues were formalized in context of agriculture. And they are again saying, look at those contexts. It also mentions about data sets. Even agriculture it encompasses many, many things. And look at this, genomic sequencing. They want agriculture to be present because plants are important, right? And then there is also test bed. They want a test bed in agriculture where all the issues discussed in ecology panels are relevant. In fact, USDA, you probably know the land grant university program. When you create a new seed, genomics is all done. That's great, but that's only half the story. You have to test it in different environment because the soil type is different. The rainfall is different and so on. So that's why you have land grant universities around the nation, and these seeds are tested all over the place. So agriculture is a community which knows about heterogeneity for a very long time, and they have worked through that, right? So it's a great part, and it is something that our federal leaders are acknowledging, right? So there are five, questions that we have posed. Some are very basic, saying within the agriculture space, what are the success stories and use cases? And we'll hear some here. And if we needed more, maybe we'll lean on Ricardo and Bob and so on to add. Then this was the basic question. I think a morning panel addressed what are the different models, and in world of agriculture, which ones are more suitable. Then going back to the challenges, we have been talking about spatial heterogeneity, which agriculture folks really think about a lot, but there are additional things. The profit margins are very thin in agriculture. So when you try to build your AI solutions, you have to be cognizant of that. And also the cost of error is very high. If the farmers makes the wrong decision during seeding, the whole season is lost. They get to repeat once a season, not once every millisecond, like what a lot of AI programs assume, right? So a lot of your reinforcement learning and so on, you have to be very careful. Maybe irrigation, you can do it, but not necessarily in seeding, right? So think about the unique challenges. And then we are coming back to the, Gen AI, saying how can, we take lessons from agriculture to strengthen Gen AI, and then building the trust and so on, which is very important in the world of adoption, right? So these are the five questions. Before the individual panel statement, I just want to give a brief glimpse of what AI Leaf is about, and then we'll go to the actual statement. So these national AI institutes actually have a broad mandate. Then beyond the research, they also have to think about workforce development, collaboration nexus, and then managing it all together. And in a way, this panel organization, which is partially supported by AI Leaf, you can think of it as in this space. So we want to actually build a community, and we have been active actually organizing other conferences. So Professor David Mulla was co-organizer of an AI for Agriculture and Natural Resources conference in April, which has now about 280 participants, right, David? And the next one is North Carolina, and year after, maybe we'll bring it to Minneapolis. So there is a community building within the agriculture space. And we hope to have a little bit of presence in the AI space as well. And in AAAI, Aryan organizes an AI for Science workshop. And next year, Aryan, what is the theme for AI for Science? It will be agriculture. Would you like to invite some people from the room to contribute and participate? Okay, good. That's a good place. Singapore in winter is a great place, right? So, this may be a little hard to read from the back, but as we were discussing the agriculture and AI, this collaboration goes back on our campus for at least 10 years. So we actually thought about, many agricultural use cases, which we confirmed through a survey of stakeholders, farmers, and so on, to make sure they were interested in these questions. But then the discussion started saying current AI, is it able to deal with all of this, or what are the challenges? So we found some limitations here, and that motivated our proposed AI research. So at least one of them, out of sample generalization, is a challenge that Vipin and others advocated, and KGML is one of the AI themes in our work. And the KGML group is very active. In fact, they are looking at some new foundation model and Gen AI approaches there. There are other systemy things here which the ecology panel would appreciate, these trade-offs and feedback loops and things of that kind, which are not very common in machine learning, also tends to be an interesting challenge. And this is just a few other activities. As I mentioned, collaboration nexus also, we have been quite active beyond other areas. So with this, I think I will wrap up the AI Leaf part and start to invite panelists to make brief statements, starting with Baskar. So Baskar, if you're willing to come here, or if you want, I can move your slides. And move the slide from down arrow if you want, or we can do
this. That's good. Thanks again for the opportunity to participate in this panel. I have the privilege to be one of the PI for one of the 5 AI for Ag institutes, which is one of the 25 AI institutes funded by the federal government, in this case, USDA and IFA, of $20 million over 5 years. And our focus within AIIRA, the AI Institute for Resilient Ag, has been on how do you integrate, and this resonates well with the discussions today, agriculture. Humans have been practicing agriculture for more than 2,000 years. So there's a lot of domain knowledge, right? Siloed knowledge, but a lot of domain knowledge. And over the past decade, 2 decades, there's been a deluge of data. So how do you fuse knowledge and data together and come up with these what we call digital twins at various agronomically relevant scales. And for us, we have two themes. At one scale of agronomic relevance is the breeding scale. So we look at modeling an individual plant in all its 3D glory. And then other is at the production scale. So we look at modeling a plot, a field, and ask a lot of what if scenarios. And this allows us to explore a lot of foundational questions in AI, but through the use case of agriculture, right? And so this is something that the fifth question of adoption is something that we have spent a lot of time thinking about. And in our perspective, the end users are at the table from day zero, which is super important in terms of framing the problems that are the pain points from agriculture, and then abstracting that to be something in applied math and CS and AI. And so our goal is to provide tools, products, and value to initially it was agriculture in general, but last year we had to put in the US part there to focus on US agriculture growers, breeders, and consumers. Especially we're getting some funding from the state of Iowa. So Iowan farmers have early adopters have first mover advantage here. And so in the context of this panel, right? So we have identified over the last 2 years, we have identified several moonshots that we will not be able to complete within our 5 years. And the hope is that the broader community can think about and contribute. And this aligns with the AI action plan that Shashi alluded to. And I'm going to have 3 slides where I talk about some of these moonshots and what are the opportunities and what are the challenges and where we are in terms of answering these moonshots. And when you say where we, I mean the broader AI and ag community, and not necessarily AIIRA, or not necessarily my research group. So the first, I mean, very quickly, right? Moonshot 1 is pests, right? With changing climate, with trade, with reduced labor, pests have become have a significant impact on productivity on the bottom line. Pests here mean insects, weeds, diseases, and so having AI-enabled tools in the hands of practitioners, growers, farmers can be a major force multiplier. That's something that GenAI tools can be a great enabler here. And second is you're collecting a lot of data at multiple scales, satellite scale, drone at the drone scale, ground-based measurements, and so on. How do you fuse these together to have actionable insight? And then the third one, I'm going to talk about the Moonshot 5 from the breeding perspective. So it's very light in text, right? So the key goal here in Moonshot 1 is, can we create tools to identify, classify, count agriculturally relevant insects, weeds, and diseases, right? So there are about 4,000 insects that are relevant to agriculture, 1,500 weeds that are relevant to agriculture across the globe. For Iowa, there's only 58 insects and about 30 weeds that are important, right? So, but then different places have different kinds of weeds, different kinds of insects. And usually what happens is, and there are several invasive species, right? So there are about 12 species that are classified by USDA and NIFA as invasive. Spotted lanternfly is an invasive species, and so on. And so rapid identification at early life stages is a critical component to taking mitigation action. And identification of insects and weeds is a non-trivial computer vision problem because of various life stages, right? You can have a nymph, you can have an adult, you can have a butterfly, you can have a moth, a lot of occlusions, right? There's also a lot of interspecies variability, right? So if you think of a beetle, you think of a beetle as something with red with black spots, but you have the same beetle species with yellow with black spots, but that's gray. So color cannot be the only possible feature to be used, right? Similarly, you have insects that camouflage, that look like other insects. And then making a mistake here can have major implications. Right? You're using too much of fertilizer or too much of insecticide, herbicide that affects the bottom line, but it also has sustainability impact. And so here, our challenge is collecting data is easy, but labeling the data is going to require a PhD entomologist level effort, right? So you have huge amounts we have created about 140 million images of insects and weeds across through citizen science efforts, but the labels of these are pretty poor. gappy. So our idea is curate the data sets. This goes back to the idea of, from the community perspective, curating in an AI-ready format, and then train what we call foundation models. So we have spent, through the NAIR project, spent about 4 months of compute on training a vision transformer with Dino V2 in a purely self-supervised way. And then we do this, what we call local to global fine-tuning. So we have this foundation model that then fine-tuned for geographically and contextually relevant applications. 58 species in Iowa, 30 species in Arizona, and so on. And then when we showed off this app that you see on the bottom left, so feel free to look at that, pestid.istate.edu. It's able to identify 4,000 insects. When we first showed it to farmers in Iowa, they said, very good, you identified the insects, so what? Right? What do I do with it? And that's when we had to add a mitigating action to it, right? That is we worked with extension folks. We're continuing to work with extension folks where we have a lot of extension data, and then that is being linked with a large language model that provides a conversational agent for farmers and growers to converse with it. And this is not a solved problem, right? There's hallucinations. How do you put in RAG? How do you put in reasoning chains so that they are comfortable? Because this is, if it hits the ground, they make decisions on whether should I spray today? Should I spray a week from now? What tank mix should I use? These are all financial and legal implications to these things, right? So we have to be pretty careful with, and that's where, again, the other question of human in the loop comes into play here. This is pretty important. And then what you see here is we also are interested in edge deployment. So this is, if this plays, does it play? No, okay. But if it were playing, it would show that we have this deployed on the on a manipulatable robotic platform that can search in the canopy to identify and count the number of insects per row, because there's something called an economic threshold. If you see 5 insects per square foot, you don't take action. If you see 7 insects per square foot, then you take action from an economic perspective. So counting here is also the point from all these things is that there's several GenAI opportunities here in agriculture, and I think this is not this is not a problem that 5 AI institutes can solve. This is a problem that the whole community has to solve, and there's a lot of wonderful opportunities. And it involves data collection. It involves major problems in AI, computer vision, and then it also involves a lot of problems in reasoning and so on. So very quickly, then without belaboring the point here, the other milestone here is how do you fuse this multimodality? And that's something that, again, will come through the discussion today and tomorrow. We have satellite data, multispectral data. We have ground-based sensors. We have time-dependent sensors that are spatially sparse but temporally dense. We have other data that is temporally sparse but spatially dense. And so, and we have other kinds of textual data. How do you fuse all these together in a consistent way? So that it provides actionable insight, right? And so again, the approach boils down to curating AI-ready data sets from agriculture, and then thinking about how do you think about these architectures, how do you think about these loss functions, and then how do you fine-tune these for downstream applications, and then how do you put this, and that's the agentic pipeline that we're excited about. How do you put this in a way that's easy for the end users to consume? Right? At the end of the day, from agriculture, it's our vision is not just write a paper and call it a day. Our vision is can we deploy these tools so that farmers, growers can actually use it and have a tangible impact on production. And then the last one, the previous two was purely from the production ag perspective. Yeah, this one is if you could rethink breeding, how would an ideal plant look like? Right? And so with gene editing, this provides an opportunity for us as computational scientists to think about how can I design a canopy of a plant, in this case a maize plant, so that I can pack more plants together per acre. It is more resilient to, say, wind events. It's more resilient to flooding events. And the way we think about this offers a lot of opportunity from generative AI perspective. How do I represent complex shapes? How do I edit complex shapes from a generative AI perspective? right? And then if I have a complex shape, can I then solve the biophysics problems on this? Can I do ray tracing to figure out how much light is intercepted by canopy? Can I do CFD by pushing in a huge, like a 60-mile-per-hour wind and seeing if the stock is going to stand or if it's going to fall off, right? And so these are all the physics, biophysics questions that we can answer. GenAI offers an opportunity for us to solve the forward models in a very rapid way that allows us to do design exploration and bring in uncertainty quantification. So with that, I think my key 20,000 feet takeaway is that we have a lot of problems, and a key part to resolving these problems is to creating AIIRA data sets, and I think the whole community has an opportunity to contribute here.
All right. So thank you, Baskar. And next we'll go to Deborah, and it will be more oral remarks. Okay. Hold on.
So I'm going to do this without slides. I'm actually going to tell you a little bit of a story. I'm a paleoclimatologist by training. I studied how climate changed in the past. When I did my PhD, I spent 99.9% of my life in a lab. I was collecting sediment cores, analyzing the chemistry, and then trying to make essentially inference about how climate has changed in the past. As a PhD student, you have to take something called a qualifying exam, which my advisor decided to describe as a medieval form of torture that every student has to go through, and it's just a rite of passage. I will agree with the medieval form of torture it was. However, I never realized how much it actually shaped my research career going from there, and that came from two questions. The first question from my committee member was, paleoclimatologists love to make that statement that looking at the past is the key to the future, but they never deliver. Like they tell you this is what happened in the past, but it doesn't really tell you how you can inform the future. How do you think you could do this with your research? Which was not something as a PhD student that I could answer. I'm going to give you the answer now. And the fact that GenAI actually allows us to do this. Once you do your paleoclimate reconstruction, you have one point on Earth in time. So then you have to work with other people who have other points on Earth in time to be able to get a field reconstruction that goes back in time. Then you can actually start using it to get a better big picture of the Earth. But how do you go from that big picture that's going to be maybe yearly resolve if you're lucky, to running an agricultural model or an ecology model or anything downstream that would actually give you any information for society? And that's really where GenAI is coming from, where you can actually try to start downscaling. It's basically a video problem. How do you actually resolve your image in both space and time so that you can actually run that information to an agricultural model, an ecology model? And that really gives you a lens into a much, much, much bigger range of climate background that you can actually use. So that was the first question, and GenAI is actually opening the door. I'm not saying it's the actual solution here just yet, but it's opening the door to actually be able to do it. The second question, which was very interesting, was, well, you do a lot of data science. How many statistics class have you taken? The answer was 1. And that's actually really something about the paleoclimatology field, is you have a lot of people with very, very different experience. You have people spending time in the field, spending time in the lab. Some people are modelers. Other people do a lot of data science. And the question is, how do you bring everyone to the table so that they can work with each other? So it is kind of a problem of working in transdisciplinary research, but here you're really working in the same field, but you have all of those different perspectives. How do you bring them to the table? And right now I'm working essentially with AI agents to actually look at how we can work with data and statistical techniques and models and actually help people create their workflow, understand the data, depending on where they're coming from. And again, this is basically facilitated by AI. So if you're a student and you're sitting in the room, you have to take your qualifying exam. Don't forget those questions. They might actually come into play maybe 20 years into your career. Thanks.
So next we'll go to David. And laser and advance slide advance.
Hello, everybody. How are you doing? Good. Has anybody in here ever hallucinated? I want you to put your one hand on the table and one hand on your chair, on the upholstery of your chair. Okay? Now tell me, how many of you think the table is colder than the chair? How many of you think the chair is colder than the table? How many of you think they're the same temperature? About 2/3 of you already hallucinated today. I'm just going to tell you that right away. So keep that in mind. If you're trying to label anything for AI, I wouldn't trust 1/3 of you. All right. So with that background, decision making in agriculture is really important. And we need lots of data, and that data has to be accurate. If we can't generate accurate data, we're going to have poor decisions, okay? Because there's uncertainty. And we have to have good data both in space and time. So we're dealing with spatiotemporal issues that are really important. And this is very complex. And I don't think that AI has adequately addressed these issues yet. But let's talk about some of the things that have worked. Bayer has a GenAI Copilot, which they trained off of an LLM-based model that ingested text. John Deere, we have a representative from John Deere here today, Demetris, who was introduced earlier. They have this weed detection algorithm. Then there's other examples. There's one from IBM. I think we have a representative from IBM here too, where they're using Prithvi W by C to do weather forecasting on the short term. And that's getting pretty good. These are all things that farmers really want. They want to be able to know what's the weather next week, not just what was it last week, because that's how decisions are made. We had, Baskar up here earlier talking about some of his moonshots, and these moonshots are really, really important. We have good examples where LLMs in ag are now becoming very sophisticated, whether they're based on text or they're based on vision. I told you about Bayer's example with, the Copilot that's based on text. And they validate this using the people that they have in their company. They ask the chatbot questions, and then they try to find out if those answers are right with the technical expertise that they have in the company. And it, over time gets better and better. There's also vision-based, examples where you can identify weeds and insects and pests. And then there's chatbots that now are actually doing pretty well on agricultural exams. Every technical service provider that works with farmers has to pass a certification test. And someone got the idea, well, I'm going to give the chatbot the same test and see if it passes. And lo and behold, they do pretty good. And when you add, retrieval augmented generation and context, you get even better. So we have some real success stories that I think are valuable to keep in mind. Now, I think the next thing that really needs to happen is for us to do a bit better job in the foundation model area, where we're trying to ingest things like satellite imagery and drone imagery and model outputs from process-based models. And so these are the training data that are used for these frontier or foundation models. But they have some limitations in how well they're able to actually, interpret images, and especially multimodal images. If we can get those models to work better, I think we'll have some really nice decision-making tools. Let me give you some examples here. So with regards to images, here are some examples of, fruit detection algorithms, which is a very difficult problem. And if you can do this from a drone, the next question would be, can you do this from a satellite? I mean, can we do this in a multimodal sense? Another question that receives a lot less attention, we talk about soil and soil health and soil conservation. These are very important for farmers, but right now there are very few tools in the GenAI world that address the questions that people have about soil. Does the soil have residue cover on it? If so, how much residue is there? Does the soil have ridges and clods? If so, how large are those clods? How much area do they cover? We can do some labeling. It's very tedious and time consuming to do this. And nobody has really taken the effort to do that. We have soils with different colors, different textures, different levels of emerged vegetation. And this is a very complex and cluttered system, which I don't think if you give ChatGPT any of these images and ask them, what is the health of this soil? Or what are the attributes of this soil that make it good or bad for farming? ChatGPT will just laugh at you and say, I don't know the answer to that. Because there's a lot of work that has to be done yet to answer these kinds of questions. If we look at satellite imagery of fields, again, this question of soil management comes back. So here I'm showing you some, SAR or Sentinel-1 images of fields, and you can clearly see that fields are different from one another. But these fields, why they're different from one another is not clear. Now, when we actually went down and looked at the soil for each of these sites, you can see very different management systems in terms of tillage and residue management. And these can be seen from the satellite, but we don't have them. We don't have the ground truth labeling to tell us what's actually going on for this complex mixture of ridges, clods, residue, soil color, soil moisture. So people have been trying in the computer science realm to use tools like masked autoencoding and variable autoencoding to interpret these. I would tell you, based on what I know, those techniques are not likely to work because this isn't like reading a book or putting together letters one following another. U doesn't always follow Q, okay? Here we have humans that are making decisions about what to do and when to do it in their fields, and these humans are not doing the same thing at the same time at the same place, and that's why you get this variability. It's not like you can mask out 3 or 4 fields and then try to predict what's happening, because it's the human decisions that are controlling what happens and not some kind of a pattern that's based on text or word order. We have these kinds of problems exist when we apply other tools like kriging. Kriging assumes certain types of spatial autocorrelation, which may not really hold when you have the humans intervening here. So we have a very human-oriented system. So what I'd like you to leave you with is a couple of needs. We need to better account for human decision-making. We don't often have access to the management data that humans are imposing on the land. And we can't just use out-of-the-shelf tools like MAE and VAE and expect that they're going to work. What tools can we develop that will do a better job of dealing with these human factors? Another thing is that we're training our AI models using existing conditions, weather, land use, soils, etc. How can these models actually be of any value if we want to evaluate what those systems would look like under very different scenarios? If the weather was completely different, or a completely different set of crops was planted in those areas for which we had no training data. How can we overcome those problems? That's a big issue. To do this properly, the computer scientists need to work with the domain scientists and vice versa, because neither of us can solve any of these problems working by ourselves. And that's where I'd like to leave you, and thank you very much.
And then Chaopeng, yeah. So there's the laser. Let's advance this.
Cool. Thank you. Hi, everyone. My name is Chaopeng Shen from Penn State University. I would like to, my slides actually answer some of the questions that was raised that were also introduction to me. I would like to introduce a method of modeling called differentiable modeling. What it is a seamless coupling, a seamless, very tight and deeply ingrained coupling between process-based equations and neural networks. So, typically when you have a supervised machine learning model, you go from X to Y. So they you learned an overall mapping and you can't understand it because maybe 20 different processes involved. However, differentiable modeling allows you to write the equations. Let's say you write down 6 of these equations and they're called priors because they exist before any learning. And the rest of the things that you're not so sure about, you replace them with neural networks and you train these neural networks together with these equations in an end-to-end fashion on big data. So for example, here I have a neural network and I have attributes and climate factors that go into that neural network, and that outputs either static or dynamic parameters, the physical parameters that is going to be needed by this process-based model, right? So the model describes, snow melt, recharge, groundwater, slow flow, quick flow, et cetera, and that gives you an observable quantity called discharge, which you can compute a loss function and backpropagate all the way on big data to train that one neural network. So this allows us to break the problem into many parts. And we say, okay, I do not trust the parameterization function, so I replace it with a neural network, right? So this is described in detail in this 2023 paper. And you can also learn unknown relationships. For example, you can say, okay, my vegetation, my plant here has acclimation. So if when I take the plant from one environment to another, the parameter will actually adapt to the new environment. So we learned that, for example, here I'm showing you that VC max 25 should really be a parameter of the environment, of the CO2, of the vapor pressure deficit. And this allows us to actually revise the estimate of global carbon cycle. Okay, this differential model is already, sure. It's not normalizing flow. So these equations are completely written explicitly as equations that are implemented on PyTorch. So you have automatic differentiation, or you solve a joint to get them, and then you embed neural networks and you connect them next to each other. You train them, end to end. So it's already transforming hydrology. So these are the 2 national scale and then global scale hydrological model. We trained this using multi-scale learning scheme. So you not only have a good training over thousands of sites, tens of thousands of sites over the whole world, but also we have high resolution output at the 6 square kilometer basins across the whole entire United States. And we see that it has very high performance. This is the traditional model, and this is we match head to toe with the state-of-the-art long short-term memory or transformer models. But you can completely understand this model, and we have high resolution simulations. We actually were doing much better in terms of the extremes. For example, here, this is a 2000 area event. We've never seen this event in a training data set. And actually, you see that multiple versions of our model was able to capture that extreme events. However, this is LSTM. So it's never seen that in the training data set. So when that happens, it kind of cowardly sticks its head out and looks around and doesn't seem right. So it retreated back to the training maximum. And that's the comfort zone of the machine learning models, right? Because it doesn't want anything that's never seen before. And all these variables such as ET and base flow, they still have physical meaning. So this is one way of coupling physics with machine learning. And I want to talk about one successful application of geoscientific foundation models. This is one model we called that's designed specifically for land. And I wanted to capture the joint distribution of the organizing principle of landscape variables. Actually, we see that this model can capture these variables, we can predict, for example, what the forest cover is using all the other environmental conditions, including climate, geology, soil and terrain data at a R square of 0.9. And what does the random forest get? 0.4. So this foundation model does capture the rich representation, and it allows us to predict what is kind of the environmental carrying capacity of the land. For example, here in China, in India, and Côte d'Ivoire, you see lush forest. That's what it should be. It is not at that much right now because human cut it down. And we think that these areas are going to be under huge climate stress. This is a very good useful use of looking at foundation models. Going forward, I think GenAI can be used for global change science. As this is actually one of the work that I've done, hearing some of the talks earlier, we can actually use GenAI to generate hypotheses. But what you can do when you have a process-based model or a more reliable process-based model is that you can actually let this AI agent run that experiment, run that model experiment, and see if it confirms your experiment or not. Right. So this is one of the ways that they can be coupled. And there's also neural operators that you can actually learn PD solutions very efficiently, 100,000 times faster than the conventional neural PD solvers. But a lot of these models, when you train it on a data basis, it gives you the right results for the wrong reasons. It has every internal relationship wrong, but it gives you an okay result. But that's not acceptable to us. So we actually, here in this work, we imposed what is called a sensitivity loss. And this is published in AIIRA 2025, this year's AI conference. So this allows you to actually refine also the sensitivity of the model. So you get a model that's not only fast, but also respects the sensitivity. This is another way of informing physics to your Jane model. You can actually, on the sensitivity level. So with that, I end it here. Thank you.
Great. So this slide again has the questions back, and several of the panelists already addressed. I'm showing a little bit of crosses here. So question 1 was already addressed by a few people, I think also David. So let me actually add some new voices here. So in the room, for example, Ricardo, would you like to comment a little bit on this from, your perspective, vantage point in ARS, and also Bob, if you are willing to say something. So Ricardo, if you can raise a hand, Shengya will bring a microphone.
Thank you, Dr. Shekhar. At least I've had limited opportunities to work with AI use cases at ARS, but I do know that there are efforts being done for helping researchers to code and translate legacy code to more modern languages. There's also efforts in order to help impute missing statistical data. So in order to strengthen the surveys that are being done and strengthen the support, the reports that they're putting out in the analyses. I think, and just a little bit outside of the research area, we're also doing operational implementations in order to summarize reports, and it's mainly RAG approaches with regards to internal documents. But I think those are at least what we're working on a personal level, though. I think most compelling success stories are definitely might have to be with guidance that can be given to farmers based on chatbots and information that they can be given to them.
So Bob, are you willing to share a little bit from the forest perspective?
I would offer that from a forestry perspective, the use of generative AI is really in its nascent stages. I think people are trying to learn what the capabilities of these tools, and I think it's interesting the different cultures, scientific cultures that are approaching generative AI. And I will say in the forestry community, people tend to be very conservative. And so anything that looks like a black box model is viewed with a great degree of skepticism. And so I think that may be impeding a little bit of the uptake of Gen AI, but I think people see the potential. We see great opportunity, particularly in answering very complex questions with respect to the state of future forests, with respect to composition, which trees are going to be growing in which parts of the country, at what rates, and can we meet demands? And so there are interesting questions about economics that also come into play as well. So I see there's more potential here than actual application, but we have very complex questions with very sparse data, and it's exciting to learn what's on the horizon.
And we are actually fortunate to have people from a third Ag AI institute. So Professor Zopar, if you want to share some of the things AgAid is thinking about.
I think I'll talk about at least a couple of things that we have been looking into and some of the challenges.
Right.
So in the stream flow prediction and water management, one thing we have been working on it, both from a modeling perspective and uncertainty quantification. Uncertainty quantification point of view.
Right.
But we have been also talking to the stakeholders in terms of deploying these tools. And one thing that they have told us is without an explainable kind of tooling added on top of this, it's a no starter for them. So, really how you can explain these models, what they are predicting. If it's transformers or some variant of it, we need to figure it out. So the explainability is a big challenge, especially when it comes to spatiotemporal kind of predictions. The other challenge, which probably we didn't cover today, is when you think about some of these farm decisions like thinning, pruning, right? The impact of those decisions are only the feedback you get at the end of the crop season, right? So that's a very, very long horizon, sparse feedback. So how do you deal with that when you want to apply reinforcement learning kind of method? So I think there are lots of open challenges there.
Okay, wonderful. So with this, let me actually open the floor for audience questions. And if we get long lulls, we'll go back to the predetermined list of questions. So please raise your hand if you would like to ask any questions in this context. Yes, okay, yeah.
I know it is out of scope of that AI Institute for Resilient Agriculture, I think it is. But water is a major focus, because 80% of the water, fresh water, is used for agriculture. Is there anything that you're doing about that?
Not our AI Institute, but there are two AI institutes which have a focus on water, and happy to have them.
Sure. Right. I think AgAid is one of them, right? Professor Zopar, do you want to comment on the water part of AgAid? Okay, Shen, you can take the microphone back here.
Yeah, I didn't follow the question fully. If you can say again, question.
Not shown there the real answers available to water.
Yeah.
Use of water in agriculture.
Yeah, so I think the water decisions are actually made at multiple levels of granularity. Is the mic on? It's on. Yeah. Yeah, so I think and lots of stakeholders are involved. So some decisions are made actually at the state level, right? Some made at the level of the districts, and then the watershed, and then basically the individual farms. I am not looking at actually the irrigation and precision related problems. We are more looking at the decisions made at the higher level up. Yeah. So I think there is probably a multi-scale, multi-agent decision making there. And even there is some game theoretic perspective, because I think all of them have to reach some equilibrium. I mean, we are not yet looking at that scale of problem. Yeah.
If that best is, are you also codifying the tribal knowledge that exists in agriculture with the farmer inputs?
That's AIIRA. That's back to Baskar. Okay.
I think, thank you for the question. That's where it is critical for us to work with the experts, right? We work with entomologists, extension specialists who have provided us documentation on what are the practices that are used to mitigate some of these, right? So there could be cultural practices in terms of rotations, there could be chemical practices, there could be biological practices, and those could be very context, location specific. What works in Iowa might not necessarily work in North Carolina, might not work in South India, right? So that's where collecting this domain knowledge and encoding that either in terms of so the three or four things that we're doing is there is yearly documents that extension specialists provide as land grant mission, but they also produce podcasts. They go on YouTube, and so that's where the different modalities of data is. We are collecting that modalities, and then we got to fuse that into the chatbot.
Right. Sure.
Here the mango tree,
Right.
they always have a neem tree.
Yeah. Yeah. Organic method. So actually on the water issue, there is one more perspective. So let me invite Professor David Mulla. There is fair amount of work on soil moisture mapping, where interesting AI has happened. So David, you want to comment on that? Yeah.
So in AI Leaf, we have a collaboration that involves Vipin Kumar and Shradeep and Sangmi Palekara from Colorado State, and Nathan Mueller from Colorado State, and myself. And we're all working on various aspects of estimating the role of soil moisture on crop production, irrigation, and ultimately, antecedent moisture and runoff and things of that nature. So what we're doing is we're incorporating process-based modeling, remote sensing, soil databases, weather databases, and then we're incorporating process-based models directly into deep learning approaches so that we can go from the surface estimated moisture from satellite imagery to deep subsurface soil moisture, which is what the plant is responding to. So we're using satellite imagery as an upper boundary condition for our process-based model that's embedded into the deep learning model. And we've published a couple of papers on this topic already, that were well accepted by the AI community. These cover the entire US and can give you daily predictions of soil moisture. So that's a big advance. We're trying as a next step to develop a digital twin for irrigation management decisions in the Western US. And just last week, we had a conversation with extension agents in Minnesota, New York, Florida, Ohio, to see if they would be interested in extending those tools to other parts of the country. And they said definitely that's one of their top priorities and needs, is getting better estimates of daily soil moisture.
So let me just add one other thing, but so some pieces are happening around water, but across 5 Ag AI Institute, the irrigation management is the neglected area. So the new efforts are needed. Is that fair? Yeah. Other questions, issues? Yeah.
So Jana just briefly mentioned this question, but so I think in this space, there are like 3 things, right? There's modeling and prediction, there's control, and there's implementation. And I'm a computer scientist. Everything I learned about farming was probably from Clarkson's farm. So no deep knowledge of any sort. So I think more than most other disciplines that I just vaguely understand, other than perhaps vaccines and epidemiology, the sense of greater good, or the third part, which is implementation, is probably the hardest here. In other words, the decisions that you make probably are for the greater good, often not for yourself. Forest fires in Canada are going to destroy air quality here. The fact that you have multifunctional buffers between your field and the next field is probably going to be good for the next field as well as your field. The fact that you use fewer fertilizers is probably going to be good for somewhere where there's runoff and bad things don't happen in the watershed down in the runoff. The bottom line of all of this is you can say, hey, if you didn't do this, good things will happen. If you leave your land fallow for for 2 years, you'll have better soil conservation in the long run, where I might not even have that farm anyway. It's not my problem. So almost all of these problems almost immediately become a mechanism design problem, as we would call them in computer science. You're trying to gain something for the greater good, but how do I incentivize you to do the right thing for the greater good? For example, you get money so that you don't grow anything in your farm, but money is a zero-sum game. Do you guys capture all of these things in a mechanism design framework and say, how do you actually implement whatever controls you think you want people to implement? Or is that a question that you say, we're not there yet, we're going to do it in 10 years?
So let me maybe just give a meta answer, and then maybe others can add. So, economics is a very key part. In fact, USDA has a bunch of, the whole agency around economics, right? And there are all these farmer incentives, as you will know, right? As you were mentioning, for conservation practices, they have been incentivized, right? So those modeling are done, both from economic perspective and the modeling perspective, right? For example, our team actually have some people in economics, right, who might think about that, right? Also, if you remember in the mission, we talked about the market, right? Whether you call them carbon market or GHG market, that's a big lever, right? And a lot of companies are interested in that. One of our partner, Indigo Ag, is about pricing into that. So the same thing when we talk about model accuracy of whether it's carbon sequestration or emission and so on, those things can help the market, because if your estimation is not accurate, there is uncertainty penalty in the market, right? So there is a policy lever and there is a market lever, and both at a very high level are something we are thinking about. So with this, let me maybe hand it over. I know maybe David, you may be closest to this, right? Yeah. Or Baskar, if you want to go next.
I can write some of my thoughts as an applied mathematician / engineer on this, right? So I think from our institute perspective, we are focused. We had to choose what our focus had to be, and our focus was stopped at the field level, right? But when we wrote the proposal, we did frame this as a multi-scale decision making process at the individual plant level, at the field level, and at the county / state level, where these questions come in, right? And so there are several other teams this is an important problem, right? Absolutely an important problem. But there's also, it's a lot of human factors that come into play here. And at least as an engineer, I didn't want to get into the human factors part of it in terms of what is the adoption, at what level of incentive would someone do something that is altruistic versus not? How does it affect the bottom line and so on, right? So I think this is ripe for the AI community to participate in terms of eliciting domain knowledge, encoding that, and framing this as a multi-scale, multiple levers, right? Where do you control, where do you observe, and all these things, right? So this is ripe for us to continue.
Okay. Just as an add-on to what's already been said, there have been some surveys conducted of people in the farming communities about their attitudes towards AI for decision making. And in fact, we have a person on our team who for the last 20 years has been surveying farmers in the US about adoption of new technology in agriculture. And in 2024, he added a new question to the survey about AI specifically, because of our, AI Leaf Institute. And the results that came back showed that over 60% of the respondents felt that there was a benefit to them of using AI for decision making. They felt confident that it would improve the accuracy of their decisions, and they were willing to try it out and use it. However, I think we have a very short window of time to convince people that that's actually true. If the tools that we're developing don't work or don't meet the needs of our stakeholders, people are going to turn off very quickly and become resistant to using AI in the future. And so we have to do a good job right now of delivering the best products possible with the highest trustworthiness possible. Otherwise, there will be a shift in attitudes. I think this is a really key point that we all have to keep in mind.
Thank you again, the panel. Learned a lot about agriculture now. Didn't know all these things. But anyway, it kind of thought occurred to me because my areas are mostly healthcare and manufacturing. So this is a lot of overlap around here. Like, for example, healthcare. I mean, if you take the plants, I don't know, do you look at the plant wellness around here? Like, if you go to a doctor, you want to have like a personalized kind of medicine. Do you have something like personalized plant healthcare? So you take the genomics and using AI techniques, you can do it. Similarly, precision is another important part of it, where you want to have accuracy. It's not only just saying that something is going to happen, but you want to have accuracy. And you mentioned trustworthiness and those kinds of things have to be there. And you have to be able to predict, like, for example, I want to predict from my ear charts what's going to happen for me in terms of my health. I can do my health profiling based on that. I want to be price efficient. Like I want agriculture people, I want it to be given to the people in a reasonable price. It shouldn't be too expensive for the agricultural folks to use it. And I want to prevent diseases for these plants happening. So it happens in healthcare. I'm not sure how much of this could be transferable. Because a lot of times what happens in scientific discovery, we kind of look at one domain, like I look at like biological domain and I map it onto the manufacturing domain. So are you kind of doing these kinds of things in there?
I can answer. Thank you for that question. Yes, the short answer is yes. And to maybe perhaps a longer answer in terms of like precision medicine, there's also precision ag, and David can talk a lot more. Yeah, David can talk a lot more about that. But here, with this ubiquitous sensing, you can actually sense the crop health, the stress state of almost every row or every plant, right? So in our AI Institute, we have a scientific advisory board, and we have Bayer and Deere, and the CTO of Deere once said that within a growing season, there are about 3 billion corn plants, and Deere measures each plant. Right. And so the amount of data that you're measuring, that you can potentially measure in terms of state, right? So you have a RGB camera, you have a hyperspectral camera that can measure the stress states. You have, we are developing these sensors that can be poked and figure out how much nitrate is being uptaken. And then these sensors can be at multiple. You have proximal sensors, you have remote sensors, and then you can ingest these and make predictions on state, right? So is there going to be and so then you can take prescriptive actions, right? So only spray this region, don't spray that region, and so yes, and we are both learning a lot from advanced manufacturing in terms of prognosis, diagnosis, and so on. But there's also unique challenges and in terms of occlusions, partial observability that are unique to agriculture that we bring to the table.
It's also going to be interesting to see the social action around activities here. Like, for example, you talk to the plants and they become well or something like that. The plants talking to other plants. Sorry.
Right. More questions? Oh, okay, Anuj.
Right. Okay. This is a general question that I want to ask to everyone about what do you think is the role of masked modeling in how we build generative models for agriculture? In the introductory remarks, we have looked at different types of data. Many of them are represented as images of insects, satellite data, and so on. And Chaopeng, you mentioned about the role of mass autoencoders in the work that you're doing. And David, you mentioned how random masking may not be the right approach because there are farmers who are making decisions. Is there a role of discovering the farmer patterns and use that in how we do mass modeling? And a related question to Chaopeng is that this entire framework of differential modeling, can that also be viewed as a way of mass modeling, that you can mask out different modules in the entire framework, in the pathway? So could that inspire new forms of self-supervised learning?
Okay.
I'll just make a short comment before you get started, Chaopeng. I think masked autoencoding works very well when you're focused on a single site and you're looking at the temporal evolution of that site. You can mask out the future climate on certain days and then estimate what might be happening before or after that. But when you're trying to predict what's happening on a spatial domain, there are some problems with that approach because of the human-induced management. I think the solution to that is to use more of the sort of inverse method, sort of knowledge-guided machine learning processes to try and infer what kind of management is happening. To me, that's what makes the most sense. And I don't think we're making a lot of progress in that particular respect yet. We may be doing it in certain areas, but there are lots of different management practices that farmers are using. And the number of management practices we're trying to estimate using the inverse methods are very few in number. So we need to expand our capabilities in that realm.
Right. So may I just add one small thing? So again, David's comment and being in the Midwest, those make sense. Here you have large homogeneous farms, right? Miles of corn. But if you go and look at farms in India or China, and you can probably imagine what I'm saying, right? There are very small patches, right? So if you try to interpolate from nearby patches, you may not get anywhere, right? Yeah. So go ahead, please, Chaopeng. Yeah.
So very good question. So about the mask modeling, the differentiable modeling has certain equations built in, and it's really emphasizing this deductive reasoning from one stage to another, and based on reasoning, right? I think in that there's certain part of that modeling it's fixed, so there's no way to insert mask. However, there are many aspects which are uncertain, and that's where you can insert mask. And I also think that the state-space learning is a way where either you do mask autoencoder or diffusion can be very useful. So we have the whole description of the state variables that comes along with the model. For example, the states of a crop, of the hydrologic system. These are all described in details by these physically based models. And suppose when we train it with neural networks, they become more realistic. Then we can have another model to learn from that. And the advantage is you can switch the order between predictants and predictors, and you can predict any missing things via association. So almost like learning on your simulation, but the advantage is you have a very detailed and realistic simulation that you can learn from. Yeah. Thanks. Very good question.
All right. More questions? Yeah, go ahead, please. Yeah.
From all of this, there are a lot of opportunity for automation. That is the reason we are doing that. Because we are doing automation, there is a data collection happening, and then we are trying to use that to see what we can do with that. You talked about pest and things which is coming at the ground level, I mean the above level, but there are a lot of things happening in the ground in terms of fungi and things. There are a lot of things that I know you know better than me. Mm-hmm. But what is the approach here? Is that we are going to throw AI at it, or there is something that a class of problems that could not be solved before or solved much better now? See, introducing a new technology into a domain is one thing, but sustaining it in a way that it has potential funding and potential industries generated through that, and also people coming into that. If you ought to say industrial Internet of Things, similar to that Internet of Agricultural Things or something like that. So what is the goal here? I mean, one is, I understand all of that, but is there something bigger picture here, or we are saying that, okay, we are going to apply AI to this?
Thank you for the question. I think there are multiple, it's a fraught question. There are multiple layers to that. So let me try to take a stab at that, right? So I think from our perspective, our bottom line is what tools can we develop that impacts, at least from our perspective, Iowa, Nebraska, and Missouri farmers, right? And so all our AI dev tools are focused on pain points that have been identified. So in terms of it's called scouting for pests, weeds, and diseases is one pain point. Similarly, hyper precise spraying, is another pain point, right? So these are the tangible outcomes that the commodity groups in Iowa, Nebraska have told us that if you are able to solve these problems, it's going to affect the bottom line for Iowa and Midwest farmers, and that's our focus. So that's the bottom line for us from our perspective. Now, in terms of your question about everything that we have talked about, at least we are doing is above ground. We have done some work on below ground feature extraction. That to me is a final frontier, right? So above ground, there's you can image, even though there's occlusion, there's a lot of interesting questions about. But figuring out how the root system looks like below ground is I mean, ARPA-E and other people have invested. There's a roots proposal. There's a lot of effort. I think it's still an unsolved problem in terms of how do you accurately and cheaply at scale figure out what the root structure of plants are going to be at over hundreds of acres. That's a frontier problem. And then
you can use the word root cause of the problem.
Root cause, yeah.
Yeah.
So I don't know, David, do you want to make any remarks? Oh, you want to go?
Take a pick at it more on a science problem. I think AI is coming into different fields in different ways. But looking at it, I think you can ask yourself two questions. The first one is, can you automate something that's painful, but it's easy enough and it's not a point at which that if a mistake is made, everything else is actually going to be affected by that? If you can answer, yes, we can use AI, and if there is a mistake, it's not a problem, it's a good start of what you want to go. The second is, do we have a method today that actually allows you to get the answer? If the answer is yes, the question becomes, is the AI method better, cheaper? If not, then maybe we should go somewhere else. And so before you get to the frontier problems and the things that are hard, you still kind of need to see if the AI is essentially able to help you with the stuff that you already are doing, but you have a validation for it, or you know that there is a way for you to say, yes, this is correct. And I think this is true for every single scientific field at this point.
All right. So let me maybe, also address it, because this kind of goes back to some things which were in the request for proposal, actually, right? So from the national perspective, there are 2-3 different ways to think about it, right? One is the global competitiveness, right? Brazil, China, right? I mean, these are big agricultural places, India. And the question is, will US remain competitive in that space or not, right? In China, they are, using AI for things you wouldn't imagine. They are on the pig, farms. They are looking at the pig faces to figure out how they are feeling, what's their health, right? So if that gives them an edge, then certainly all the pork exports, right, from Iowa and elsewhere could be affected. Brazil is competing in a big way, right? So the one is to stay competitive. That's number one. Okay. Second, in terms of actual economics, there have been success stories. Precision agriculture is one of them. David was at the forefront of it. And in fact, large companies like John Deere, tractors and so on, they have all switched to that. They have GPS. And there they can actually show both. So when you do precision agriculture to apply fertilizer and pesticide only at the places where you need to, it has dual benefit. Your actually productivity goes up. You can actually count the number of bushel per acre and it's up. And your losses go down. Your water quality is improved. But all those fertilizer going into the water is economic loss, right? Farmers are just losing money, right? So there are industries like that. But precision agriculture initially was mostly adopted by large farms. For a smaller farm, they tried precision ag as a service, prescriptive farming. And that's, I think David can tell us how successful it is. It's still in work in progress, right? So there are some real things. You can look at even economic perspective. The carbon market or GHG market I brought up, maybe for now, US federal folks may not be as excited, but there are many people around the world, and it's a massive economic opportunities, right? Whether you sequester carbons in the forest, right, or through the soil or other places, there are billion-dollar startups forming everywhere. If you can, their main hiccup is, can you quantify them more accurately, right? Private sector is willing to put in money, and there are a lot of companies around the world who want to buy carbon credit. Tesla won't be profitable, right? That's a DoD success story, but they make losses. But $400 million per year they get on carbon credit, right? And so just imagine if all the forestry companies and so on, what kind of credits they can get if the quantification can be more accurate, both in current terms and long term, right? So there are massive economic stories. There are massive international political stories in this space. And a lot of that is in the RFP, and the NIFA leadership can do that, yeah. So I think we are inching to the end. So any more comments or last closing questions? Go ahead.
Can I just very quick comment? So the standard AI, ChatGPT, do things that humans can do at a cheaper cost.
Right.
But I think as scientists, one thing that really interests me is to ask AI to do things that we were not able to do. And it does it at a better job. That's what excites me. For example, we were never able to do these parameter calibration well. And actually in one of the national agencies, all they do every day was doing calibration ad nauseum. And actually with this AI that I showed, we can train this model that knows how to do parameterization. And once you're done, you can generate the parameters for the entire United States within like 5 minutes. Like that's just amazing efficiency. And it can evolve at such a rapid pace. The national water model has had 6-7 years to evolve until this point, whereas we only work on the project for 1 year. Really, that it evolves at a minute scale, right? So it learns from data at a minute scale. So the efficiency of that is also quite fantastic, amazing. So it delivers a lot of benefits.
Right. And I will add just one more, which may be a surprise to many people in the room. Typically, when AI comes up, we are all worried about job losses, right? But in agriculture, the story is different. Agriculture actually has labor shortage, and farmers are aging. In fact, ag aid colleagues will tell you that many of the specialty crops, they don't have the labor workforce to go pick up the fruits. So many farmers are changing crops because they don't have enough hands. So if you can bring up robotics, you can bring up some automation, you would actually, even right now, right? Your PI tells how many apples are not picked, right? So right now, I'm saying you're throwing stuff down the road because you don't have the labor force. If you can get the robotics and other things to work, your manufacturing thing, if you can get these machines to go and pick out the nuts and apples and all the fruits, there is money there right now, So there are a lot of economic incentives. Yeah. Good. Any last questions or closing comments before we wrap up? Yeah. Okay.
A quick question, maybe. I hope so. I was listening to Baskar's comments earlier, and he described how the moonshine #1, right? How to disentangle different kinds of pests, the insects, and so on. And I'm in astrophysics. I hear people talking about, okay, we get astrophysical imaging data. How do I disentangle different types of transient sources? So to what extent can we take, for example, your models in agriculture, take out a beetle and put in a supernova and get an astrophysics model? And if that works, can we think about putting data sets together and training larger models, benefiting from all of that all together, all at once?
Well, thank you for that question. I think that's a very interesting question that we should write a proposal on. And so my take, and this is, I'm thinking on my feet here. I've not thought deeply about this. At least from our experience, from a self-supervision perspective, a lot of data is awesome, but performance after the self-supervision stage comes from fine-tuning on very domain-specific data. And so training these large models on very diverse data is definitely a possibility. And I'm assuming astrophysics will get hundreds of terabytes of data for something like that. But then fine-tuning has to be very, very domain-specific, right? And then the point about multiple characteristics, right? So you have gravitational data, you have other data. So that's also something hopefully the material science group will talk about tomorrow. And even in material science, you have different ways of characterization, right? So you have spectroscopic, you have microscopic characterization, you have other kinds of characterization, which are different views of the same object, and then you have to disentangle that and construct it. So I think there's a closer bridge between materials and astrophysics than astrophysics and agriculture, but happy to chat.
So I think I want to jump in and say one thing. Actually, I was thinking about this topic. I think, in our way of training neural operators, we're training a neural operator on one equation, and that equation only. But if with a foundation, I'm thinking about if like a foundation model that trains a neuron operator that can be trained on multiple equations at once. And then you have the equation annotated, so it knows, okay, when you give me this equation, I got to do that. When you give me a hyperbolic equation, I got to, let the wave travel, right? So then you can potentially have a foundational neural operator that potentially knows how to interpolate between the equations, right? That would be very fantastic to work on.
Cool. All right. Okay. Wonderful. So a lively discussion. So let's thank all the panelists and everybody who asked a question in WhatsApp.